the role of 8257 DMA controller is basically, as its name suggests, it is DMA, that is direct memory access. So if the memory of the 8085 need to be accessed by the external device, then there is a need of DMA controller. What it does is basically a microprocessor is there. This is microprocessor and this is external device. Okay. So, and this is slow and this is fast. So as microprocessor is fast and it is slow, so to communicate between external device that is slow and microprocessor that is fast, basically it is not an efficient manner of data transfer basically. So even if the microprocessor is fast, as the slow device, the external device is slow, the data transmission will only be taking place in slow mode only, so that the speed of microprocessor will be limited. Okay, so that is not an efficient way to transfer the data. So basically for that we will be requiring a medium or intermediate component. Okay, so that intermediate component will be 8257, that is called DMA controller. So here DMA stands for direct memory access. Okay, so direct memory access means, so microprocessor is having a memory. Okay, and from this memory a data to be transferred to the external device or external device to memory. So to communicate between these two components, memory of the microprocessor and external device, to communicate between these two devices, the use of DMA controller is basically exists. Okay, so here what DMA basically does is it acquires the control bus, data bus, and address bus of microprocessor, and based on the requirement of the data, based on the requirement of external device, DMA controller itself controls all the buses and makes sure the data can be transferred from memory to the external device. Okay, this DMA controller basically designed by Intel with respect to the data transfer. This is the fastest way to transfer the data, so it gives fastest data transfer rate. Okay, and it allows uh, the device to transfer the data directly to or from the memory without any interference of the CPU. That means the microprocessor will not be interfering in the data transfer. The directly DMA controller will be able to transfer the data from the memory or to the memory. So using DMA controller, the device requests the CPU. So how does it works basically? So what this DMA controller does is it requests the CPU. First of all, the DMA controller will request to the CPU to hold the data address and control buses. That means first of all, DMA will request to the CPU like you need to hold accessing or using these buses. So basically, if the data address and control buses is free from the interference of microprocessor, okay, then these buses will be free to transfer the data from the memory of the CPU basically. Okay, so the DMA data transfer is initiated only after receiving the HLDA signal from the CPU. So this we will be seeing like once the DMA has sent a request and microprocessor or CPU has acknowledged that request, and that acknowledgement will be in the form of HLDA. Okay, so this is hold acknowledgement. So CPU will provide hold acknowledgement, or the microprocessor will provide hold acknowledgement. Once the hold acknowledgement signal is received by the DMA controller, the DMA control starts transferring the data from the memory by using the data address and control buses to the external device. Next point, we will see how a DMA operation is performed. There are following steps basically. This is the external device. First of all, the device that we need to communicate with the memory of the CPU. So that device will send a DMA request to the DMA controller. Okay. So then another DMA controller, and here the external device. Okay. So when the external device need to access the memory of CPU, what it does is this request will be basically called DMA request. This is called DRQ. Okay, so external device will send a DMA request to the DMA. Okay, this is the first step. Next, the DMA controller sends the hold request to the CPU. So once the DMA request is received by the DMA controller, that is sent from the external device, then DMA controller will send a request to the CPU. Okay, so this send a request will be called as hold request. It is sending a request so that the CPU can hold, or the microprocessor can hold the accessing of data control and address buses. So this is hold request. It is called HRQ, hold request. So this DMA will be sending hold request to CPU. So once this CPU receives this HRQ, that is hold request, what it does is, by completing its task, once it has removed the control to the buses, this CPU or the microprocessor will send a signal back. So this signal will be basically called the hold acknowledge, because it was hold signal was requested by DMA. So in acknowledgement to this hold signal, the hold acknowledgement will be sent. So it is called hold acknowledgement. Once this DMA has received the hold acknowledgement signal, now the CPU is working in hold state. That means it will not be controlling the data bus, control bus, and address bus. So at that time, once the hold acknowledgement has been received with the DMA controller, that means the DMA will be whole sole controller of basically the data bus, address, and control bus. So once DMA controller is able to control this buses, it will be performing the memory or data transfer from the memory of the CPU to the input output device, or whatever device it is. Okay, these are some features of 8257, that is a DMA controller. In terms of features, if we say, it has 4 channels which can be used over 4 input output devices. That means 4 signals, 4 input output devices can communicate at a time, can send data to 8257. Each channel will be having 16-bit address. Okay, so it will be having a 16-bit address. Okay, so address will be of 16-bit, and it will be having 14-bit counter. So basically this counter is for like how many bytes of data need to be transferred. That will be decided and stored in this 14-bit counter. So here each channel can transfer data up to 64 KB. So each channel can be programmed independently. So based on the requirement and what are the applications, how we need to connect, we can program the each channels. Each channel can perform read or write, and also it can verify whether particular operation has been taken place or not. It will be generating a mark signal to peripheral device or external device if 128 byte of data have been sent. If 128 byte of data have been sent or transferred, then the DMA controller will generate a signal that will be considered as the mark signal. So mark signal is basically one of the pin output of the DMA controller that will indicate like the 128 byte of data have been transferred. DMA controller will be requiring a single phase clock, and its frequency ranges from 250 Hz to 3 megahertz, and it can operate in 2 different modes. So one is master mode, another one is slave mode. So these 2 modes are there. We will see that later. This is the pin diagram of 8257 DMA controller. We can see like total, starting with 1, there are total 40 pins, and this pin at the left bottom is your ground. Okay, and your basically with respect to that, we will see like whatever input we are providing, that will be in the form of request to the DMA controller. So here is like request are basically, because it is 4 channels, so it will be receiving the request from the external device by 4 different input, 4 different. So these are like DMA request, DRQ 0, 1, 2, 3. So four, these are channels. So these are pins that are indicating the channels, like the 4 pins are there. So these 4 external devices, infrared devices can communicate, send a request to the DMA controller. And these requests like D0, D1, D2, D3, it has some preference also. So there are some preference. There are some preference to DRQ signals. We will see that later. So once the DRQ signal has been received from the external device by the DMA controller, it will send hold signal to the microprocessor. Okay, so it will send hold signal to the microprocessor. Okay, and if that hold signal it has sending hold signal, or we call it hold request. So hold request is basically HRQ. Hold request is there. So this is the hold signal that will be an output signal from the DMA controller that will be going to the microprocessor. Okay, microprocessor hold pin. It will go to microprocessor hold pin, and once the microprocessor has stopped the control of uh, different buses, it will send HLDA. So HLDA will be output signal for the microprocessor, but it will be input signal to the DMA controller. So once this HLDA have been received by the DMA controller, now the DMA controller can control the data and address and uh, control buses of the microprocessor, and it can now either read or write. So if it is reading, okay, if it is reading uh, with the input output devices, so it will be for input output read. This is input output write. This is memory read, memory write. So if it is reading the data from the input output devices, it is considered as reading from the input output devices. Okay, so IOW, that means input output write. So it is writing the data from the input output devices, then that pin will be activated. Okay, in case of memory and read and memory write, so it will be a input signal. This mark signal, it is pin number 5. Mark signal, we have seen this mark signal is basically used when 28 byte of data have been transferred, then mark signal will be okay. And here de acknowledgement. So whatever request have been sent, that is device request that have been sent. So to acknowledge the devices, there are 4 different acknowledgement. So if the 808 8257 is ready to transfer data between the memory to the input output devices or the external device, it will acknowledge the device by using these acknowledgement 4 acknowledgement signals 0, 1, 2, 3. And here pin number 31 will be giving you out the VCC. So these are different bits like data bits. So it can transfer the 8-bit data. So D0, D1, D2, D3, D4, D5, D6, D7 as given by this. Okay. So addresses are there, A02, A7 up to here. Address bus are there. Okay. They are the different pins of 8257. And this is the architecture. This is the architecture of 8257. So in this 8257, there are 4 different channels. So these are channel 0. Okay. So one channel will be having a DRQ request, that is DRQ 0. That means it can accept data from the external device. Next one is it will be giving acknowledgement to the external device. The next channel 1 is there, channel 2 is there, channel 3 is there. So channel 1, channel 2, channel 1, channel 2, channel 3. So for all different channels, it will be having a 16-bit address and 14-bit counter. Each of the channel will be having. Okay, and it can accept the DRQ request, and it will give a device acknowledgement Okay, and there is a priority resolver. Okay, so this priority resolver will prioritize whether the request from which channel will be considered first, and if all the four channels have given the signal or the request, then which signal need to be processed first. So that is decided by the priority encoder. One block is control logic and mode set registers. So here this is another block that will basically set the logic and the control of the DMA function, either it is working in master mode or slave mode, either it is uh, how it is going to transfer the taking the data, how it will be accepting the you can say permission to access the buses basically. That is decided by this control logic. Okay. Next one is read write logic. So read write logic is basically it will be providing the read write signals. The next one is data bus buffer. So here in case of data bus buffer, it will be sending the data to the data bus. So this one is basically the data bus. So these are the description of 8257 pin basically DMA request. So external device is sending four different requests can send at a time. In that, it is basically sent by the peripheral devices for using a DMA service. So if a peripheral device wants the help of a DMA controller to transfer the data, then it will be sending a request to the DMA controller, and then the DMA controller, based on the availability, it will give the permission to access the DMA controller to the buses basically, and then the data from the memory of the CPU can be transferred to the input output devices. So here, when the fixed priority mode is selected, when there is a fixed priority, then DRQ0 has the highest priority and DRQ3 has the lowest priority. So if we are going with the priority, so DRQ0, DRQ1, DRQ2. Okay, so this will be having highest priority, and as we will be going down, it will be having the lowest priority. So this is basically dealing with the priority. The DMA acknowledgement lines are there. So these are the active low DMA acknowledgement lines. Basically, if the external device send a request to DMA, with respect to this DMA request, the DMA controller will send a JRQ, that is hold the request signal to the microprocessor. Microprocessor will be acknowledging with HLDA, and once the HLDA has been acknowledgement made by the microprocessor to the DMA controller, then DMA controller will be sending back a signal to the device. Like this signal is called DACK, that is DMA acknowledgement. D0 to D7 are bidirectional data lines which are used to interface the system bus with the external bus of the DMA controller. IOR is input output read. Okay, IOW is input output write. So it is a clock having a clock signal which is required for the external operations of 8 to 57. So whatever external operations we need to perform, then the clock of 8 to 57 itself can be working as the clock signal. Okay, so this 8 to 57, that is DMA controller, has its own clock signal. This is CS, that is chip select basically. So it is active low pin. If it is active low, then chip will be selected. So this ready pin is there. So this of ready pin, it is an active high asynchronous input signal, which makes DMA ready by inserting wait states. And this active high pin basically synchronizes the input signals that is available to the DMA controller. So in DMA controller, once this signal ready signal high, then it will make the DMA ready by inserting wait state. The next one is HRQ that we have already seen. That is hold request. Hold request will be sent to the microprocessor from the DMA controller. This HLDA is the hold acknowledgement. If DMA controller has sent HRQ, that is hold request, microprocessor basically. Once the DMA controller sends the signal to microprocessor, whatever request will be there. After performing its operation, the microprocessor will remove the control from the buses basically. So once it has removed the control from the buses, it will send hold acknowledgement to the DMA controller. The memory read, the reading the data from the memory. Okay. The next one is memory write. So it will be like the DMA controller will be writing data to the memory from the external device. Okay. So this is ADST. So this ADST is basically we call it strobe signal. Okay, address strobe signal basically we call it. So this signal is used to convert the higher byte of the memory. So as we know, the memory is of 16 bit here. So in case of DMA controller, memory is of the channel. Memory has 16-bit address. Okay, so in this address, the signal, this address stop signal basically is used to convert the higher byte of the memory. So this memory there, so it will be 8 bit, 8 bit. That means 1 byte, or we call it lower byte, and this is higher byte. 1 byte instruction will be memory space will be there. So this signal is basically convert the higher byte. So it will convert the higher byte of the memory address generated by the DMA controller into the latches. So whatever the higher address bytes are there in the memory, that will be converted as a latch. It will be, once it is activated, it will be sending the input data to directly to the output data. So that is the role of address adjustment, address strobe we call it, strobe signals we call it basically. AEN. So this AEN, this signal is used to disable the address and data bus. So basically it is address enable. So this is address enable. So if it is high, that means address will be enabled. If it is low, it will be uh, working as a data bus. So this signal is basically disable the address and data bus. So as data and address bus are basically multiplexed buses, as it is multiplexed, that means if it wants to work as a address, then address enable pin should be high. The next point is TC. So this TC stands for terminal count. Okay. So basically it indicates the present DMA cycle to the present peripheral device. So whatever this is the terminal count. So whatever the present DMA cycle is there, along with the peripheral devices, whatever peripheral devices have been connected, that will be giving out the terminal count. Okay, it basically indicates the present DMA cycle. So, in what particular cycle the DMA is working, that is considered given by the terminal count. This mark we have seen, if 128 byte of data have been transferred, then this will be activated. This mark pin will be activated. This is VCC. Okay, you already know what is VCC. So up to now, this is the basics of 8257, that is DMA controller. So in DMA controller, basically we have seen what are the of DMA and how architecture of DMA controller is there and how different functionings are performed basically. So data bus read write function and different channels it is having. Okay, so different channels are used to connect a particular peripheral device so that it can communicate through these channels and connect with the memory of 8085 or microprocessor basically. So all these we have seen. So next we will see how the working of this 8257 is basically going to take place. So in this working of 8257, we will start with different type of registers that is available to 8257. So 8257 and 8237, these are complement they are almost the same name is there. Okay, so it is either written as 8257 or 8237. Okay, there are some differences, but most of this properties of these two ICs are same. Both are for DMA controller only. Okay, so here the DMA controller is basically, we have seen here in the architecture, like it is having different registers. Okay, so it is having 16-bit register. So this was the 16-bit register and a 14-bit uh, counter. So this counter and uh, address lines are there. So this is 16-bit address lines, and this register counter is the register available to this DMA controller. So there are different registers available to DMA controller. So these registers address is basically given by the A0 to A7 bit. Okay, so different A, so A0 to A7 bits is going to give the address of different registers that is being used in DMA controller. So in that, the bit A4 to A7 is going to indicate like it is working as uh, a uh, let's say the chip select for selecting the different registers. So here this chip select is being controlled by this chip select is controlled by uh, A4, A5, A6, and A7 values, and this combinedly considered as chip select, and the remaining lower nibble, we can call it lower nibble A0 to A3, based on different values of this, starting with 002 up to 1111. There are different addresses that is going to give different registers address. Okay, that is available to DMA controller. Okay, so this complete list we can see from here. So overall, we can see. So here, so based on the chip select, how the chip select will be activated. So once this A4 to A7 bits are going to help for controlling the different registers. So different registers will be selected based on the values of A0 to A3, and the chip select that is consist of like having the registers. The chip select will be activated based on the A4 to A7 value. The chip select will be enabled by this configuration that is being used by a decoder, and based on the values of A0 to A3, different registers will be selected. So in that registers, if 00 is there, then that will be indicating uh, channel 0 memory address register. Okay, so channel 0 memory address register means here memory address register basically indicates the location of this indicate the location of starting byte. Okay, so which data, the data that should be copied to the external device or the peripheral, that external peripheral can be a floppy disk also. So if a floppy disk is connected, then what is the, suppose this is the data that we need to copy to an external device. Okay, and the starting address of the data is whatever like AA is there. Okay, if that A address is there, or suppose 4AA, that is 16-bit address that should be there. This 16-bit address is there. That address location will be indicated starting with the first 8 means 1 byte. 1 byte will be indicated here. Okay, by the memory address. Okay, so this memory address, channel 0 memory address will be indicating the location of the starting byte of the data that to be copied. So its starting byte will be indicated in the register that is given by that register address will be given by 00. Similarly, 01 will be giving you out the count register. So this count register will be going to count based on the byte. So suppose we have known like one channel of DMA is basically going to transfer maximum 64 kilobyte of data. Okay, so 64 KB of data. That means for 64 KB of data, there should be 16-bit address line. So that 16-bit address lines will be there. Okay, so we have seen like a channel is having basically 16-bit address lines. So that in that address lines, to that address lines, the data channel 0 will be going to transfer the data up to 64 KB. Okay, so starting location of the first byte that need to be transferred will be stored in 00 location, that will be for channel 0, that is called memory address register, and 01 will be indicating like for channel 0, this is the count register. So count register will also be of, you can say, the 16-bit. Okay, so that is going to count the byte that need to be transferred. So once the starting address has started transferring the data, the counter will keep on decreasing, keep on reducing. So once the counter had reduced to 0, the data transfer will be stopped. That means that much of data has been transferred that was required. Okay, so whatever byte of instruction byte of data need to be transferred, that count is stored into the count register of that particular channel. Okay, so similarly, if it is 02, that 02 address location will be giving you out like it is the channel 1 memory address register, and 03 address is channel 1 count register. Okay, so similarly, there are different registers available to DMA controller. So that registers is basically having a particular address that a DMA that can be accessed by the instructions. Okay, so these instructions can access these address locations so that data can be transferred directly to these registers. And next, we have seen different signals of, or you can say different pins of 8 to 57, or we call it 8 to 37. Okay. So in that, there are different signals we have seen. So we have seen AEN and ASTB. So ASTB is basically address stroke. So what is the use of address stroke and AEN? Okay, so this address enable, so address enable and address stroke. These two are combinedly used to decode the higher byte of gives a higher address lines basically. So these are A8 to A15. So A8 to A15 will be basically controlled by the latch. So this first latch will be controlled by this first latch, and this first latch will be enabled or controlled by the pins, that is address enable, okay, and address strobe. Okay, so these two are there, and to select the lower byte of the address, so lower address lines A0 to A7, only the AEN, that is address enable, will be required. So once the address enable is enabled, that is it is made to 0, this latch will be indicated activated. So once this latch is activated, so whatever address lines are there, that AD0, that is multiplexed address lines are there. These address lines and data lines, in that these data lines and address lines that is multiplexed will be working as the data lines. Okay, so to have this latch enabled, AEN should be activated. Okay, along with that, it is going to control by the ALE. This ALE is of basically 8085. It is ALE pin of 8085. So if the this 80 to 87 is connected with 8085, so this, if it is working as a address lines, this should be activated as a address. So to have that address activated, ALE pin should be high. So once this ALE pin is high, this latch is enabled. And also, if AEN pin of the DMA controller is 0, by combining ALE and AEN, this multiplex address and data lines will be working as lower byte of address lines, so basically lower address line. Okay, and lower address lines will be activated by ALE and AEN, and higher address lines will be activated by address strobe signal and AEN, that will be activating this. Okay, and that will be connected to here. So the lower address and higher address can be activated by 80 to 87 only. Okay, and different signals we have already seen. And at the end, once the data transfer of DMA controller has been completed, it gives end of operation signal. So once end of operation signal is activated, that means the data transmission through the address lines have been completed. Okay. Next, we will see how different modes, basically the modes of DMA controller. So in the modes of a DMA controller, so in the previous class also we have seen that there are two different modes. So one is slave, another one is master. Okay. So one is slave, another one is master. So in slave mode means the data transfer should be taking place between the microprocessor and the DMA controller. If data transmission is taking place between microprocessor and DMA controller, at that time this DMA will be working as a slave mode, working as in a slave mode. If DMA controller is going to transfer the data between the external device, okay, and it is communicated with memory of, I can say, a microprocessor is there, and this is usually the memory. Okay, so data transmission between memory to external device is taking place through DMA, then it will be considered as master mode. Okay, so if microprocessor is transferring data to DMA, it is considered as the slave mode, and in that we can see, like, we can make sure like this is the memory. So data transmission is being taken from the memory to the this, and there is a control signal. So data lines and bus lines here in this mode, the DMA controller will be controlling the data lines, bus lines, and address lines of the microprocessor also. Based on that, it will be generating the control signals, and that through that control signals, there will be a direct transmission, direct transfer of data from the memory of microprocessor to or memory, external memory to the external device. Okay, so memory, whatever memory is there, through this the data will be transferring. So this is the master mode. Okay. So here in slave mode, basically the DMA controller is treated as a peripheral. So here in case of uh, slave mode, if it is working in a slave mode, that means the DMA controller is going to work as a peripheral device, like the external device that is connected. It is similarly going to consider as a peripheral device, such that it is communicating between the microprocessor only, microprocessor and the DMA. If these two are communicating, that will be considered as the master mode. So here there are different steps. So in master mode, basically the microprocessor unit selects the DMA controller through the chip select. So the first step, like in that, the microcontroller, the microprocessor is basically going to select the DMA controller basically through the chip select signal. And once the chip select signals is activated, the DMA controller has been activated, then microprocessor will be writing some control bits to the DMA controller. So that control bits instructions are basically given in the example that we have considered in the down below. So we have seen that example in the down below. We have included that example. Okay. So here, so first, whenever some processing is going to happen, the microprocessor will be selecting the DMA, and it will write some instructions, some control words to the DMA controller so that it can perform a particular selected operation. Okay. So once chip select has been activated and microprocessor is writing some data, that data is in the form of control bit, like it will be a controlling bit for the DMA controller. So that control bit writing to the DMA controller by the microprocessor is basically up to that it is considered as the slave mode. Like the peripheral, it is working as the peripheral device because it is only receiving the data. The DMA controller basically in that slave mode is going to receive the data. It will not be transmitting the data or doing any operation. It will be just uh, storing the data or storing the control bit, control data given by the microprocessor. Okay. So here the microprocessor writes the control word in channel registers and command status registers. So different registers are there using the control signals input output read and input output write. Like so microprocessor will be writing the data to the DMA controller through the command and status registers that are available to the DMA controller. So that mode will be considered as the slave mode. Okay. So in the next, that is a master mode. So basically in the master mode, so in master mode, the DMA controller will be the whole soul and it will be communicating within the external device like a floppy disk is there. Okay. So there will be taking communication between these two and data transmission will be taking place between memory. Okay. So here DMA controller is the main unit. Okay. So here that's why it is called master mode. So once the initialization, so the slave mode, we have seen the slave mode. So once the slave mode has been completed, so whenever the DMA controller is going to operate, the first operation will be the slave mode. It will be initially operating in slave mode such that some data should be written to the DMA controller. Once the data has been written, that is called initialization. So initialization of the DMA controller. Once the initialization has completed, then the DMA controller basically enters into the master mode. Okay. So once it is entering into the master mode, then it will keep on checking is there any DMA request is there or not. So if there is DREQ, so it will once the initialization has been done, it will keep on checking for any signal that is uh, available to DMA request or not. There are different DMA requests based on a different four different channels. Okay, so in that it will be giving this waiting for different commands. Okay, so here once uh, the different commands need to be completed, so there are different steps that should be followed. So it will be keep on waiting for the DMA request. So when the peripheral is ready, so when any external device is there and that wants to communicate or that wants to transfer the data or accept data from the memory, then the peripheral device will send this DMA request. So once initialization of a DMA controller has been done, and the peripheral wants to transfer the data or take the data from the memory, then it will send the request to the DMA controller. So that will be in the form of DMA request. So here, basically, when the peripheral is ready for data transfer, it sends high signal to D request. Okay. So whatever D request signal, that is DMA request signal is there, that will be made equals to 1. That will be made equals to 1. So once this DMA request has been made to 1, then so here this signal that is given by the external device, that will be DMA request, DRQ basically. It will be given to the DMA controller. Once this DMA controller has received this DRQ, it will say to the microprocessor, so this is microprocessor, it is going to say the microprocessor like what need to be done is like once the external device has requested for DMA request, that means the floppy disk either wants to send the data, receive the data. So it will DMA will send the data to microprocessor as hold signal to be sending, and this hold signal is for like it is going to the microprocessor should be holding the control of the data and address buses basically and control buses, so that a DMA controller can access this that buses and send the data directly. Okay. So once DRQ request has been reached to the DMA controller, okay, the particular channel, so whatever channel is there, that channel will be enabled and the control logic sets HRQ, that is hold request. So hold request will be generated. Okay, so once DRQ has been received, the channel will be activated and the hold request will be generated. That will be in the form of like it will be made to high. So this high is connected to hold signal of the 8085. So this HRQ request is connected to the hold signal of the 8085. So that hold signal will ask to the microprocessor like the DMA wants to have the control of the uh, data and address bus and control bus basically. So in the next cycle, the microprocessor unit relinquishes the buses and sends the HLDA, that is hold acknowledgement signal to the 8237 or 8257, that is GMA controller. Okay, so here once the signal hold signal has been received by the microprocessor, it will uh, relinquish means it will give the control of the different buses and sends once it is going to give the control, it will send the signal HLDA. Okay, so once the HLDA is received by the DMA controller, then the DMA controller will enable the AEN. Okay, so this AEN will be enabled high. So in the previous slide, previous page that we have seen, so this once the acknowledgement, hold acknowledgement has been received by the DMA controller, this AEN pin will be activated. Okay, so once AEN pin is activated, that means the first, that is AD0 to AD7, that will be connected of the microprocessor will be connected to A0 to A7. Okay, so here this is high. This high means the latch 2, the above latch, the first latch that is at the top, that is latch number 2. That latch number 2 will be basically this the high signal AEN will disable this latch. So the first top of the top latch will be disabled, and thus this connecting the demultiplexed bus A0 to A7 of the MPU and enables the latch 1. Okay, so latch 1 will be enabled and this latch 2 will be disabled. Okay, so once this latch is enabled, so the in the next the DMA will set the address strobe. Okay, so address strobe signal will be made high. So once address is high and AEN is high, at that time the lower byte that is made to high. Okay, so here we can see, so this is high, that means it is after inverter it will be low. So if it is low, this will be activated and this is address stop is there, then the this latch number 1 will be activated. Latch number 1 will be activated, that means the higher byte or higher address lines will be connected to the AD0 to AD7. Okay, so here the next that is connected to here, then the this latch will be enabled, and after enabling that, that means whatever data is there to the AD0 to AD7 pin, that will be placed to the higher byte of the DMA basically. Okay, so higher byte of DMA means it will be with A0 to A15. So whatever data is there on AD0 to AD7 will be placed to this address. Okay, so higher byte of the data is being placed here. Okay, and at the same time the DMA also outputs the low order address. So low order address and high order address both will be activated. Okay, so once the low order address and the high order address both are activated, then the complete 16-bit address will be activated. Okay, so once the complete 16-bit address have been activated, that means once the address is activated, then whatever the data is there, then the DMA basically once this address is available, address lines up to 6 bit, then DMA will acknowledge to the peripheral device like it is it has completed all the setups to complete to transfer the data. Okay, so once the DMA is ready with all the configurations, then it will send the DACK, that means DMA acknowledgement to the external peripheral device, and that external peripheral device that can be a floppy disk or any other device. Okay, so once all the settings have been done by the DMA controller, it will send the DAQ, signal to the peripheral. Okay, so once the DAQ signal is sent to the peripherals, now the role of DMA is like, based on the request, whatever the control bits are given to the DMA controller, based on the control bits given, it will be either writing or reading the data from the input output or memory devices. Okay, so based on these signals, it will be giving out performing some operation, and this operation will be performed till the DMA acknowledgement is high. So once the DMA acknowledgement is high, and this will be remaining high till the data transfer have been completed. Okay, so at the end of the data transfer, the DMA control will, once the desired amount of byte have been completed, and the transmission have been completed, then it will uh, give the signal end of operation. Okay, so this end of operation, that is a low signal, that will be informing the peripherals like the data transfer is complete, and now the data transfer, that is basically uh, transmitting, that will be completed or it will be stopped as the end of operation is activated. Okay, so end of operation has been activated, then the stop, it will be stopping the data transfer. So this mode is basically considered as the master mode. Okay. So once the microprocessor having no role, only the DMA controller is going to perform the operation, then that will be considered as the master mode. Otherwise, if the DMA controller is being receiving the data from the microprocessor, then that mode will be considered as the slave mode. So whatever mode is there, okay. So first of all, if we are going to take the help of DMA, okay, then the first step will be slave mode. Okay, so once the slave mode has been completed, the step 2 will be, it will be going for the master mode. Okay, so, and in slave mode, the microprocessor is going to send the data to the DMA, but in case of master mode, the DMA is going to send the data to the peripheral devices or external devices. Okay, so next we will see that example. Okay, so in that example here, some DMA initialization instruction need to be run. Okay, so like how the initialization is basically done by the microprocessor for the DMA controller. Okay, so here initialization is being done such that the following conditions should be met. Okay, so based on the following conditions, how the initialization should be done. So here, here it is given like use of same port or register address between 00 to 0F need to be done as we have seen in the above register list, total register list. Okay, in that. So here the first instruction is like disable the DMA controller and begin writing initialization instruction. So first of all, it is saying disable the DMA controller and begin writing the initialization. Okay. So once it is the next one is initialize channel 3. So channel 3 we need to initialize and transfer 1 kilobyte of data. So 1 kilobyte of data, that means we need to transfer the data. So once the starting address, okay, so here starting address is given. So like we have given this starting address, this. So starting address is this 4075. Okay, and 1K byte of data need to be transferred. That means to have 1K byte of data, that means 10 address lines are there basically. So starting with if in terms of 16 bit we can write. So 4 bits are here, 4 4 4. So for basically for 1K, that means 2 to the power 10 is there, 1k is there. Okay, 2 to the power 10. So 10 means starting with 0 0 0 0 to 0 0 0 0 0 0 0 0 0 0. Okay. So suppose this is the starting byte location. The end byte location will be like up to 10. 10 bits will be high. So up to here it will be high, and the remaining bits will be low. So starting with this address to this address, there will be a total 1k byte of data will be there. So starting location we can see is like 0000 h. So the end location should be like 0. In case of here it is 0, and this one is 0011. That means 3 is there. 3 is there, and this is f. This is f. Okay. So to transfer the 1k byte of data, okay, 1k byte of data, the starting address would be here and the ending address would be here, or we can see like the counter. Okay, so here basically we need to put the value of counter. Okay, so count register should be there, so the count should be having the location of 03FF. So if this is the value of count register, okay, and if one byte is transferred, it will be reduced to by one, and again next byte is transferred, then it will be reduced to minus one again, and once it is zero, that means the complete 03FF byte have been transferred. So based on the count register value, the DMA understand whether still it needs to transfer the data or not. Okay, that means in the count register we have to put the value 03FF. Okay, from here we can see, and here the starting address of the data block that need to be transferred. So whatever block is there, so the starting address of the data is given by 4075H. Is the starting address is 4075H, and it, based on that it will keep on accessing the address. So, okay, so this is the starting address, and the next data that need to be transferred is above this address. Okay, so this is 4075, so 4076, 4077. So these are the data from here up to here. 1k byte of data need to be transferred. The next address will be higher than the 75, 76, and 78, and so on. It's given in the condition. Okay, and now the next condition is 9. Like the command parameters should be like normal timing, fixed priority, late write, D request, and both are active low. So these are the different command lines that need to be activated by the data that we should be or the microprocessor should be writing to the here. So that is, you can say, more in broader sense. We have not considered that part, like how the control words are basically given, how the normal timing and fixed timings are there. That we will, that is not part of our syllabus basically. So we are just understanding like how the microprocessor basically writes the data to the DMA control. Okay. So here next is set up the command mode, set up the demand mode whereby the DMA can complete the data transfer without any instruction. So we need to set up this command basically. So here for initialization, first of all is like the DMA is being disabled. So to disable the DMA, this data need to be sent to the accumulator, and that accumulator will be sending the data to command register. So here in the register part, okay, so here in this register part, it is 08 address of the register is considered as the read write status or command register. Okay, and also this count register is there because we are selecting, we need to select the channel 3. So channel 3 count register location is 07, so that we will be sending the data here, and to select the channel 3, 06 is the location. So these three will locations register addresses will be written there. Okay, so we will be sending the first one. So this is to disable the, this is the command to disable the DMA. So this disable command that will be written here, that means this, the data that we are providing is in the form of bits. Okay, so 8 bits that we need to be providing. So this 8 need to be 8 bit need to be provided to the accumulator. So we will be moving this mvi command a comma this data will be moved to accumulator. This accumulator is for 8085. It is accumulator of 8085. So whatever accumulator data is there, that need to be put out to the address location or the port address that is given by 08. So 08 is the location of the command register of DMA controller. So we will be sending this data to the command register of DMA controller, that is out 80H. So this means the data have been sent to the DMA, like the DMA need to be stopped. So this is for the disabling the DMA. Okay. Next is now based on the mode. Okay. So based on the mode that we need to activate. So in that mode, so control word we have not seen. So based on the control word, like if it is writing or reading the data, if it is writing the data, 01 should be given. Okay. And if channel 3 need to be selected, 1 should be provided at the lower byte, lower data, lower 2 bits. And this auto load is been disabled, so it is 0. If increment address is there, then it should be 0. And it is demand mode, then it should be 00 mode. Okay. Demand mode means it is we are providing the data to the basically DMA controller. Basically, it is demanding. So this is how the control words are selected. So once this mode have been selected, dash data that is 0000, that means 0, and this is 7. So 07 data, or in either we can write 07 in the form of hexadecimal, or we can write in the bit format also. That should be moved to the accumulator, and this accumulator will be writing this data to 0BH. So 0BH location that is given here basically in case of the register. 0BH is write mode. Okay, so write mode register. That means once we are going to write the data, the microprocessor is going to write the data that will be given to 0B location. So it is writing the data to the DMA controller. It is going to give the data to the 0B location. So once the it is written given, that means the DMA need to perform the different write data operations. Okay, so to write the data, starting byte of so from there from which location data should be written. So this location address should be provided to the channel through which we are going to take the data transmission. So in that the location is given like 4075 was given in the question. So first of all we will be sending the lower byte. So lower bytes need to be sent. So 075 value will be put into the accumulator, and this accumulator data will be taken out to the port address. That port address will be 06. So 06 is basically for the channel 3 memory address location. So this is memory address register is there, that is given for the channel 3, that is 06 is there. So to the address, memory address of the channel 3, lower byte will be sent first, and then the higher byte, that is 40. So we need to send the 75 first and then 40. That means the complete address have been sent. So by these two instructions, we have sent the complete address. So once the complete address have been set, now we will send the control count bit basically. So count bit we have selected like with there for 1k byte, 1k byte of data, we should be having the count like 0, 3 and FF. So first we will be sending the lower byte, that is FF, to the count register of channel 3. So count register of channel 3 is given at 07 of the address line, that address location in the list there. So we will be sending the count value lower one first, and then the higher one we will be sending, that is 03 location. Okay, to the 07 location again. So once we have done this, now there are different writing like in what mode the this DMA controller should be writing working. Based on that, there are some selections that like DMA is enabled, and once it is enabled, in what mode or in what condition is to be working, that is given into the question itself. So from there it is selected. So this control word status basically we have not gone through in the deep. That is for basic understanding only. Okay. So that data, whatever data is there, that will be written to the accumulator, and this accumulator will be sending this data to the 08 location. So 08 location is basically for the command register basically. Okay. So this command register, once we need to send some command to the DMA controller, we should be sending the data to the 08 port location. So that means that will be considered as the command to the DMA controller. Okay. So this is how the initialization basically is done. So this is the initialization. Okay. Initialization of the DMA controller. Once the initialization has been done at this is at that time, whatever time we are performing, the complete time is considered as the slave mode. Here the DMA is working in a slave mode. Once the command have been sent, now the DMA is enabled and the command is sent to enable the DMA. Once the DMA is enabled, now whatever operations will be performed, that will be considered as like the DMA is working in master mode. Okay. Now the DMA is working in a master mode. Okay. So this is how the DMA basically works. Okay. So up to here, the DMA part we have completed.